Today we talk about the algebraic techniques of finding limits, but let's just quickly review our graphical method of finding a limit. Once again, the concept of that limit is as x gets close to a certain number, what does y get close to? So in this case, we're going to look at this function over to the left and find the limit as x goes to -2. Well, as I move towards -2, from the left direction and the right direction, as you can see in the green arrows right here, what we want to be doing is we want to be approaching the same number. Now, from the left direction, we seem to be getting very close to -1 for a y value. From the y direction, we seem to be getting very close to 0. Since they don't approach the same number, there's no limit. As we approach 3 from both sides, I'm approaching 3 from the left, and I'm approaching 3 from the right, and we notice that our arrows are headed towards the same point, that point being -2. So we say our limit's equal to -2, even though the value at that point, we know f of -3, or f of 3, sorry, is equal to 1. Now, we're going to talk about limits of continuous functions. First of all, let's define a continuous function. We're going to use more of a non-mathematical definition of a continuous function. We'll get our mathematical definition later. A function that is continuous is a function that has no breaks, no holes, or asymptotes. So you can draw the function without ever lifting your pencil. It just keeps moving. If a function is continuous around a point where you're trying to find the value of a limit, then the limit of that function can be found by direct substitution. In other words, if we want to find the limit as our x value goes to some constant of a function, then all we need to do is plug that constant into the x value of the function for every x that exists. For instance, I have an equation here of a line, and we know that this line looks something like this. It's continuous. I can draw it without lifting a pencil, no holes, no asymptotes. And since this is a continuous function, and I want to find the limit as x goes to 6, basically, I just find f of 6, which is 2 times 6 minus 8, or in this case, 4. Likewise, I have a polynomial function here. It's going to look something similar to this if you know its end behavior. And I can draw that without lifting a pencil. And if I want to find the limit as x approaches 1, all I need to do is find f of 1. So that's plugging 1 in for every x value. And, whoops, it's positive 1. And if I grind all this out, I get 1 minus 2 plus 5 minus 10, which gives me a total of -1, positive 4, -6. So limits can be as easy as direct substitution, just finding f of c, but they may get more complicated as well. Let's take a look at this problem. Now, I don't want to necessarily have to graph this to be able to find the limit if possible. What I'm looking at, clearly this is probably not a continuous function. In fact, let's just graph it for kicks and talk about some pieces of it. At 2, I get a graph that looks similar to this here with an open circle. And then I have a value at 2 and another value that moves when x is greater than 2. So you'll see the graph's not continuous. However, look at where I'm trying to find my limits. Where this graph is discontinuous, in other words, where it breaks, is all at the point 2. At every other point, the portion of the graph is continuous. So within that region, those graphs are continuous. And I'm trying to find the limit as x approaches 3. Well, x approaches 3 is in this limit here, or in this interval. So really, all I have to do is find the value of the graph at 3 in this region, and I'll find the limit, since it's continuous from 2 over. So if I find f of 3, that's just equal to 3 squared plus 5 or 14. When I want to find f of -5 lands somewhere over here, and I know that's in this region. And all I need to do is find f of -5 to find the limit. F of -5 is going to be 9 in this case. So again, even though this function was not continuous, it was continuous at the point where we're trying to find the limit. These functions we don't know a whole heck of a lot about. However, we do know that this function is going to be continuous at 1 because the only thing that makes this undefined is when I get negative values. If I look at the domain of this, 5x minus 4 has to be greater than or equal to 0. So x is going to have to be greater than or equal to 5 for my domain. And then the function's defined everywhere else. So if x has to be greater than or equal to 4/5, and I'm looking for the limit as x goes to 1, I can simply find f of 1 to find the limit. So when I do that, I get 1 minus 2 minus 1 quantity cubed all over square root of 5 minus 4. And that's going to end up equaling -2 cubed or -8. So that will be the limit of that function. In this function here, I notice I have to be within a certain bound to make sure this is defined. Let's just make sure when I plug a -1 in, I don't get an undefined term. Plugging -1 in, I get 1 plus 5 plus 2. So this function is clearly defined at -1, and it's defined in regions outside of -1 on either side. So if I just find f of -1, I can find my limit in this case, which again is going to be 8. Now, when we have limits at undefined values, in other words, we're trying to find a limit at a hole or at an asymptote or some place like in a piecewise function where the graph breaks, we've got to take some things into consideration. When that x value is not in the domain of the function, that's that undefined value, you've got to simplify the function and determine if that undefined value is a hole. And if it is a hole, then we have to say what x is getting close to, which would be that whole value. So for instance, here's a function. If I were to graph it, I know I'd want to factor the numerator. And we notice that x plus 2 reduces, which means I have a hole at -2. But if I have a hole at -2, that means the function is undefined at -2, but the limit will remain the same because this function reduces to x minus 2. I'll have a hole at -2 and -4. And you'll notice as I move to the left and move to the right of -2, which is where I'm trying to find my limit, my function actually approaches the hole's value of -4. So we say the limit as x approaches -2 of this function is -4. And we did that once again by factoring and reducing and finding out where that hole was. Let's take a look at this problem. We look at what we're approaching, in order to find our limit, and that's -3. If I take -3 and square it and subtract 9, my denominator is undefined, which means hopefully this will reduce, because otherwise I'm approaching an undefined value for my limit. Let's try to factor. We notice in the numerator we have x minus 11 and x plus 3, and our denominator is x minus 3 and x plus 3. Factors of x plus 3 reduce, which means our function is now x minus 11 over x minus 3. We're trying to find the limit as x approaches -3. We know there's a hole at x equals -3, and if I want to find out where the graph of this function, and keep in mind this is going to be some kind of a rational function where I have a y-intercept of a little bit over 2. It's going to look something similar to this. But I'm going to have an undefined value at -3. So somewhere over here I'm going to get a hole. The question is, where is that hole? All I need to do is plug my -3 into my remaining value here, and I'll have my limit. So what I have now is I'll take the limit as x goes to -3 of x minus 11 over x minus 3. It's now defined, so I get -3 minus 11 over -3 minus 3. It ends up 14 over 6. Since they're both negative, I can reduce that to 7 over 2. And that's where that hole will be, roughly at 7 over 2. This function also is undefined when x is equal to 0. So I'm going to need to simplify it, and it's a complex fraction. So in order to do that, I'll add the numerator, add the denominator, and take the reciprocal. So I have the limit as x goes to 0 of 2 over 2 times x plus 2 minus x plus 2 over 2 times x plus 2. And that's all over x over 1. Adding like terms, you'll see here that as I distribute the x through, I get a negative x over 2 times quantity of x plus 2 all over x over 1 multiplied by the reciprocal. I get the limit as x goes to 0 of negative x over 2 times x plus 2 multiplied by 1 over x. Notice the x's will reduce, which gives me the limit as x goes to 0 of -1 over 2 times the quantity of x plus 2. Now you'll notice after I've reduced this function, since the x reduced out, I can now plug the value of 0 in and get an answer out. So it created a hole, I just didn't see it. Therefore I have -1 over 2 times 0 plus 4, which is -1/8, and that's my limit. This problem is the trickiest of them all. When I plug in a 9, you'll see that I have an undefined term. I don't know how to graph this, but I know that this is going to create some kind of asymptote most likely, or possibly a hole if it reduces, but I don't see necessarily a factoring from here. What I'm going to do, and typically this is the trick for most of these, when you see that you have a binomial in the denominator that has a radical in it, you're going to want to rationalize by the conjugate. So I take the limit as x goes to 9 of 9 minus x over 3 minus root x, and rationalize by the conjugate of the denominator. It's 3 plus root x. to both the numerator and denominator. Notice what's going to happen. I'll have the limit as x goes to 9 of, I'll leave this as is for the time being, 9 minus x times 3 plus root x. In the denominator, I multiply by FOILing, I get 9 plus 3 root x minus 3 root x, that goes to 0. And I'll have minus square root of x squared, which is x. So now you'll notice that the 9 minus x is a like factor which reduces, leaving me with the limit as x goes to 9 of 3 plus root x. So whenever we reduce factors, we have a whole, and again, we didn't know what that looks like because we never really graphed something like that. And to fill in that hole or to find out what x approaches, I just plug in the x value, which I can now do because my denominator doesn't go to 0. And I get 3 plus root 9, which equals 6. And there's my limit. In this next problem, we're going to find the limit as x approaches 3 of the average rate of change of the function. Well, again, let's talk about the average rate of change. That's just our slope. And in order to calculate a slope, we just take f of x minus f of b over x minus b, or y2 minus y1 over x2 minus x1. Applying that to this problem, we're finding the limit once again as x approaches 3 of this slope. So f of x is negative 2x squared minus x plus 5. I can find out what f of 3 is. Let's just plug that in. That's negative 2 times 3 squared minus 3 plus 5 gives me negative 18 minus 3 plus 5, which is negative 16. So I want to go f of x minus negative 16 over x minus b, which in this case is 3. Simplify. Take the limit as x goes to 3 of negative 2x squared minus x plus 21 over x minus 3. The problem is I can't plug a 3 in, so I'm hoping this numerator is going to factor. Let's go ahead and give it a shot. Take the limit as x goes to 3. I like factoring my negatives out, and I get 2x squared plus x minus 21 all over x minus 3. So the limit as x goes to 3 of opposite of 2x and x. We need positive 1 and multiply to 21, so it's 7 and 3. Let's go 7 and 3 here, positive, negative. So luckily it factored in such a way that factor that I needed to reduced out. So I have the limit as x goes to 3 of negative 2x plus 7, which is just the negative of 2 times 3 plus 7, or negative 1. And that's all we have for today. Fill out your summary form, do your My Math Lab, and we'll discuss this more tomorrow.